In this video we're going to look at the initial value theorem. Now the idea behind this is that you can find the initial value in the time domain of a function by looking at how the complex frequency domain behaves at infinity. Okay, so now we looked at that in a previous video. Okay, so now if we were to take a function, say g of s, and we did the Laplace transform of it, also if we looked at a function g of t, and we Laplace transform the function g of t, okay, to give the function g of s, then if we were to then look at the limit as s tends to infinity of this function g of s, then we could write that down as the limit as s tends to infinity of the integral from 0 to infinity over g of t e to the minus st by dt. Now we know that there is going to tend towards 0 because as s tends to infinity, this whole value e to the minus st tends towards 0, so the whole thing will tend towards 0. But what we're interested in here is not the Laplace transform of g of t. We're interested in the Laplace transform of a derivative, so we'll call the derivative function f derivative of t. So what we're interested in is taking the limit as s tends to infinity of a function, and the function is the f derivative of t e to the minus st by dt. So we're interested in taking the Laplace transform of a derivative and taking it as the limit as s tends towards infinity. So we've already seen the Laplace transform of a derivative. Okay, so if we take the limit as s tends to infinity of the s f of s, now sf of s minus f of 0, okay, this section here is the Laplace transform of a derivative. Again, we derived that in a previous video, so you can go back and have a look at that. So again, this thing here is going to be equal to a value 0. So what we can do is we can now transpose this. Okay, we can take the f of 0 over the other side, so we're then able to say quite simply that the f of 0 equals the limit as s, a bit of space there, the limit as s tends to infinity of s f of s. Okay, so that really is the initial value theorem, that little snippet of information. So it allows us to find out the initial value in the time domain of a function without doing the inverse transform of the function from the complex frequency domain back to the time domain. So an example of that would be, and these things are best seen by example, if you had a function f of s equals 1 upon s minus a, and that's a is less than 0. Again, we've seen that function before, and we've actually drawn it out in MATLAB, so you can have a look at that in previous videos. So now we're able to say by this initial value theorem, we can find the value of the function of time of this complex frequency function, and it's the initial value of it in the time domain. We can find that by taking the limit as s tends to infinity of our, it's going to be s times that, so it's going to be s upon s minus a. So we're just taking that function and multiplying it by s, taking the limit as s tends to infinity. So that there, as s tends towards infinity, the limit of that there equals 1. Okay, so the result is that the initial value of this function here in the time domain is 1. Okay, and now that function there in this instance here, that f of t actually looks like f of t equals e to the at times u of t, and the value of that function when at t equals 0 is 1. Okay, so we've used this theorem in order to find out the initial value of a function in the time domain when all we know is the complex frequency domain representation of the function, and we don't need to do that inverse Laplace transform to find it. Okay, so that final value theorem is useful in order for solving an awful lot of problems there quite simply. And whenever I go through a playlist on the Laplace transform examples, we'll see quite a few examples of that. Okay, so thank you for listening and goodbye.